Start with a coin model. The dial is its probability of heads. Set it to 1/2 and look at the next 4 flips. 4 tails is possible. 2 heads and 2 tails is more likely. 4 heads is possible too. 1 parameter setting gives a distribution over many possible observations. Turn the dial toward heads. The bars for head-heavy datasets grow while the others shrink. Turn it toward tails and the pattern reverses. The parameter is fixed while we ask what data it might generate. A different setting gives a different distribution. This is probability's forward question. Choose a model, then ask what it predicts. The arrow runs from a fixed parameter to possible data. Likelihood begins after one of those possibilities has actually happened. We observed heads, heads, tails, heads. Pin those outcomes to the screen. They will not move again. Now move the model's probability of heads dial at every setting. Record the probability assigned to the same fixed sequence. Near 0, 3 heads are hard to explain. Near 1, the single tail is hard to explain. The curve rises between them and peaks at 0.75.
Why does the other display say 0.105?
0.75 is the chance of 1 head. The whole sequence has probability 0.75 cubed times 0.25, about 0.105. Horizontal position is the parameter. Height is the probability assigned to all 4 observations together.
Isn't this still probability?
It is the same formula viewed in reverse. Fix the parameter and vary the data, probability model. Fix the observed data and vary the parameter, likelihood. The formula did not change, the question did. Each flip contributes 1 factor. A head contributes the probability of heads. A tail contributes 1 minus that probability. 3 head factors and 1 tail factor multiply into the probability of the fixed sequence. As the dial moves, that product traces the likelihood. Multiplication uses an assumption. Once the parameter is fixed, the flips are independent. If flips influence one another, these factors no longer multiply this way. A likelihood is the model's assumptions made visible, not a generic score pasted onto data. Large products are awkward. So take a logarithm. The product becomes a sum with 1 log contribution per observation. The peak stays in the same place. This log likelihood is easier to compute, and later becomes the loss used by much larger models. Mark the highest point. For 3 heads and 1 tail, it lies at 3/4. That point is the maximum likelihood estimate, or MLE. Useful but compressed. One number cannot show the curve's width or asymmetry. Change the data to 4 heads. Now the curve climbs all the way to 1. The maximum sits on the boundary, not atop a tidy hill. The peak exists, but its surrounding geometry tells a different story. Keep the objects separate. The likelihood is the whole observed landscape. The MLE is 1 landmark. On it, first build the landscape. Only then decide what question to ask of it.
Is likelihood the probability of the parameter?
No, a probability model fixes the parameter and distributes probability across possible data. A likelihood fixes the observed data and compares parameter settings. Its heights need not add or integrate to 1. The comparison also inherits the model's assumptions. If flips influence each other or the probability changes over time, this coin likelihood is wrong. Likelihood compares possibilities inside a model. It does not certify the model itself. One observed likelihood can support several questions. A likelihoodist compares relative heights. A frequentist studies an estimator across repetitions. A Bayesian combines the likelihood with a prior. The MLE matters, but it is one use of the curve, not its definition. First build the landscape, then ask your question.